Let's welcome the next speaker. Next speaker is Tian Song, and his paper is PtCAM, Scalable High-Speed Name Prefix Lookup using TCAM. So Tian Song is a professor with the School of Cyberspace Science and Technology at Beijing Institute of Technology, China. He received his Master of Engineering and PhD degrees in computer science from Tsinghua University. His research interests include information-centric networking, high-speed packet processing, and network security. Particularly, he's among the earliest scholars studying named data networking since 2010. In his talk, he will present the team's recent work, PtCAM. PtCAM addresses the critical challenge of high-performance name prefix lookup in the next-generation network architecture. Please.
Okay, thank you for the introduction. Good afternoon. I'm Tian Song from Beijing Institute of Technology. Today, I'm happy to present our work named PtCAM is a scalable high-speed name prefix lookup using TCAM. So, in modern networks, actually information is always paired with its names. For examples, if we consider the content delivery network, URLs are the names of the contents. If we consider the information-centric networks, so we have the contents and also have their names. Even we consider the peer-to-peer systems, the hash values are their names. While devices are connected via IP addresses in network layer, content has long been exchanged by names in the application layer. This motivates the design of information-centric, a future internet architecture built directly on content. Routing in ICN is based on name instead of addresses, and efficient name prefix lookup becomes the key enabler. So, in IP networks, forwarding relies on IP addresses, and the longest prefix match problem has been well studied. But in ICN and content delivery systems, routing is based on names, not IP addresses. This introduces new challenges. So names are much longer and variable in length, and the namespace is much larger than IP addresses. This difference makes traditional IP lookup techniques inefficient for name prefix lookup. So let's compare IP routing with name-based routing more carefully. As for January this year, the global IP forwarding table contained about 972,000 IP prefixes. With such a limited namespace, the solution is straightforward. We can use TCAM as it can achieve fast line speed, line rate, and bitwise parallel lookup. So if we can consider the name forwarding in contrast, like we use the DNS domain names, for example, the DNS domain names already exceeded 750 million entries. That is almost 3 orders of magnitude larger than IP space. So if consider that space, the TCAM is too small to store hundreds of millions of prefixes. So all existing solutions explore SRAM, DRAM, or even GPU to do the lookup. But their lookup speed often cannot keep up with the increasing line speed. So here we arrive at this question. What kind of hardware devices can provide the most advanced speed for name lookup if DRAM and SRAM cannot catch up with the line rate? Surprisingly, our answer is still TCAM. We know TCAM offers line rate parallel lookups and have been widely deployed in today's router. However, I think we need to redesign how we use TCAM to make it feasible for massive scale name prefix lookup. So TCAM is temporal content address memory. As far as I know, I think it's a dedicated device only useful in IP lookup. So let's look at the scalability issue more closely. The large name field with unbounded length names requires a large amount of memory. A large name field with tens of millions of prefixes and average length of 32 bytes would require several gigabits of storage. This exceeds the capacity of commercial TCAM devices. So the key challenge becomes, how can we compress and reconstruct names so that TCAM becomes practical for name lookup? So we gave our solution PtCAM, short for PtCAM. So let's look at the basic PtCAM overview. Our goal is to look up names directly with TCAM and then fetch the address for further lookup in DRAM or SRAM. Actually, it's a hybrid solution. Through RAM access, we finally obtain the forwarding phases. So what we are stored in TCAM as RAM is very important. So we gave, the idea is to extract a kind of compile name and to store them in TCAM, and we put all the token of the forwarding information table into SRAM. So TCAM acts as a high-speed classifier, while RAM stored the full tokens for verification. Thus, PtCAM has two stages: processing stage and also verification stage. So the hybrid design allows us to achieve constant time lookup while overcoming TCAM's limited size. Let's move on to the first processing stage. So at the heart of PtCAM is a data structure named the binary PtCAM. Actually, binary PtCAM is an old-style data structure. We use it to build from the name prefix. So this data structure can actually is a try-style, and in the internal node is a kind of discrimination bits that can separate different names. Let's take the two names like Google and the YouTube. So there are two name prefixes. If we look at the 43rd position from the beginning, we find that in this position, we can classify these two name prefixes. If we go, if the value at that position is 0, it maybe go to the Google side. If the value is 1, it will go to the YouTube side. So we find that the binary PtCAM can find the criminal position, bit position that classify all the names. So we use that features to build the binary PtCAM from a full table, a name table, and then we construct the compact name table. Is to the compact name table, we call it CNT, is the storage for compiled names extracted from the PtCAM. So we only store values at criminal positions. So our contribution is that we can rebuild a kind of compiled name from the root of binary PtCAM to the node, to the leaf node, and we got a kind of different kind of name, a short name, a compiled name for the long human readable names. So we got a compiled name table. This greatly reduced memory size, since the number of critical bits is typically much smaller than the full name length. In effect, CNT bridges the original FIB and the TCAM representation. After we built the CNT with binary PtCAM, then we gave the memory layout for TCAM and the DRAM. So we put all the CNT entries into the TCAM. So since they're different, the compiled name of different name prefix have different length, so we fill empty don't care into each entries. We also gave the full tokens into the RAM side. So finally, after constructing the PtCAM structure, we load it into both TCAM and SRAM. And from this point, the system is ready for high-speed name prefix lookups. So the lookup process is simple but powerful. For each incoming name, we extract its compact name, the criminal bit positions, and put it into the TCAM. And the compact bits are searched in TCAM in only one cycle. And TCAM returns the RAM address of a candidate prefix, which is then verified in RAM. Thus, each lookup only requires just one TCAM and one RAM access. With pipelining RAM to catch up the speed of TCAM, since TCAM always faster than RAM or SRAM, so PtCAM can ensure very high throughput. So after this basic PtCAM, we also gave refinements to PtCAM. So we gave three refinements, so I will explain them one by one. So the first one, we called it PtCAM with equivalent position. Let's look at the PtCAM with equivalent position. In a particular try, some criminal positions may overlap in functions. So compare the left side. Actually, in the try, we have 4 different criminal bits. That is position 43, 44, 45, and 47. And actually, to see the right side of the try, we can use the position 44 to distinguish the two entries. And also, we also have the equivalent position, like 45. It can also distinguish the two right side two entries, two names, name prefix. So we can use the equivalent position to reduce the number of the criminal bits we required in our systems. So from this example, we can reduce the TCAM memory from the 4-column to 3-column, with us about 25% memory advantages. And also, the second requirement is to PtCAM hash, which use prefix hashing to balance the particular try. So we know that the try, if try is balancing, it will use much less bit positions. So we do the calculation of hash calculation for the name prefix if the prefix is component-based. So after that, we build the particular try. We can use fewer the bit positions to arrive the results. And the third requirement is we call it PtCAM sub. That is designed to push scalability even further. This idea is to split the particular try into multiple sub-tries, and we prompt sub-tries and allow TCAM to only index the entry point of the sub-tries. So after that, the prompt try is small enough for TCAM, and each try is stored, can be managed in RAM. So if the try is smaller enough, so we can use one or several fewer memory access to RAM, and to get the small amount of memory, get a very high speed. So PtCAM sub also enables us to cascade multiple PtCAM instances. By using that solution, we can scale up to tens of millions or even billions of name prefix. So this approach makes PtCAM practical for extremely large-scale deployments. So then we conducted extensive experiments to evaluate PtCAM scalability and the performance. So first, we gave 5 data sets we used, including 2 human-readable real-world sets and 3 random synthetic generated data sets, scaling up to at least 50 million names. We developed a custom site compiler that converts name data sets into particular try and compact name table formats, and even we gave the memory format for TCAM and SRAM. So the compiler is usable. We also open source the compiler, and the community can verify, replicate, or even extend our results. So let's look at how PtCAM reduced TCAM usage. We can see that with refinements of both hash and equivalent position method, PtCAM compressed it site Alex, which contain 1 million names, as well as 16 million bytes, and into very few sites, about 240 megabits. After another observation is that PtCAM can accommodate more random names compared to human-readable names, because random names generate more balanced tree and require fewer critical positions. That is, give us more advantages. Next, we analyze how PtCAM scale with this size. We can draw several important conclusions. First, the required TCAM size is linear to the number of names. Second, both PtCAM, the refinements can improve memory efficiency. Moreover, the right figure show that a very interesting results that if we take about 8 to 10 cranial position as reserved in the TCAM for updates, it can support around 20% of name updates in real world. So our analysis also explains why human-readable names are harder to handle. Like the left side, the figure is a human-readable size, so we can see that the trie structure is imbalancing. And if we use hashing and if we use the generated rules, and the trie is much balancing, so we can get the better results. So we finally evaluate the scalability of PtCAM sub with different sub-trie sizes with data-driven analysis. We find that the results show that PtCAM requires only 20 megabytes RAM to accommodate 1 million rules, and also around 100 million bytes to reserve to support the 3 million rules. So we also, besides data-driven analysis, we also evaluate PtCAM with real hardware. So we implemented PtCAM as a forwarder on an IP LAN card equipment with IDT 75K TCAM, which has a size of 18 megabits. The results show that the lookup speed of PtCAM can reach around 5.8 million search per second at the 4 gigabits per second wire speed. However, we didn't get the more higher speed because that's the limit of the hardware interfaces. So that means we can achieve more performance. So we further analyze the potential lookup speed of PtCAM based on the parameters of the hardware we use. So that's from the analysis. We conduct a numerical simulation to make the potential lookup speed analysis under the assumption that the requires are randomly dispatched to DRAM, and the PtCAM system with enough number of parallel DRAM, like 25, may support to reach up to 500 million search per second. It's very huge. It can support maybe 500 gigabits per second LAN speed or even more. So we find that our method, if give enough DRAM parallel, we can get a very high speed to do the name lookup to support the information-centric or other network usage. So to summarize our findings, PtCAM is scalable and efficient in terms of efficiency. With our refinements, and 80 megabits TCAM can accommodate millions of names, achieving maybe 120% capacity improvement. In terms of scalability with sub-trie refinements, a small TCAM can support tens of millions or even billions of name lookup. And furthermore, PtCAM is practical for real deployments. That's we can use the commercial TCAM devices, even using an IP LAN card to do the name prefix and also to do the rapid networking innovations. And the PtCAM can also be applied to other domains that rely on string or prefix matching at high speed, so such as CDN, software-defined firewalls, and DPI, and other solutions. So we also have some future works. That's all my talk. I'm happy to take any questions. Thank you.
In the interest of time, we can have one question. Have any questions from the audience? Can't see any. I think like one question from me is that looking at this work, how is your experience on updating these TCAM entries? They say you have some changes in your entries that you need to recompile it and then install. Is there an incremental update process, or like update is super fast? What's your opinion on this?
So if you update, you will have to incrementally build the try, project try. And you will find that if we reserve some bit positions, there will be open space for you to update this one into the TCAM as a new column. So that will be online very fast to do the updates. So our results is that only 8 to 10 reserved bit that can support about 20%, maybe if 1 million size will be 200,000 updates, that's enough.
Okay, thank you. Cool.